I'm Gene Kopp, and this is a video abstract for the paper Generating Weights for the Weil Representation Attached to an Even-Order Cyclic Quadratic Module by Candelori, Cameron Franc, and myself. The main theorem of the paper determines the weights of the generators of a particular graded free module over the ring of modular forms. Specifically, the module of vector-valued modular forms transforming by the Weil representation. Our result holds for Weil representations attached to cyclic quadratic modules of order twice a prime power, for a prime at least 5. The Weil representation attached to a lattice was used by Borchards in the theory of Borchards' theta functions and Borchards' products. Our exposition of the Weil representation relies on an equivalent formulation by Skarupa and Stromberg using finite quadratic modules. The Weil representation is a finite-dimensional representation of the metaplectic group MP2Z. It may be described explicitly by the image of the generators S and T of MP2Z, as shown in the slide. We can interpret weakly holomorphic vector-valued modular forms of weight k as the global sections of a line bundle, Vk of rho. However, to specify a holomorphy condition at the cusp, we need to use something called the compactified metaplectic orbifold M1/2 bar. There are multiple ways to extend Vk of rho to M1/2 bar, and they depend on a choice of exponents, meaning a matrix L with eigenvalues in a specified interval I, such that rho of t equals exp of 2 pi I L. To obtain the standard definition of holomorphy at the cusp, use what's called a standard choice of exponents, one where I is the half-open interval from 0 to 1 containing 0. The lengthiest computation in the paper is the calculation of the trace of L for the Weil representation. This computation recovers some classical results that rely on the Dirichlet class number formula. One is that, if P is a prime congruent to 3 mod 4, there are more quadratic residues than non-residues modulo P in the first half of the interval from 1 to P minus 1. Another is the less well-known fact that, when P is 1 mod 4, the same is true for the first quarter of that interval. For both facts, no purely elementary proof is known. The computation of trace of L leads us to formulas for the multiplicities of the generating weights that involve class numbers of imaginary quadratic fields. We make the observation that no generators appear in weight 23 halves, even though general theory doesn't disallow this. Finally, we give the limiting distribution of the multiplicities as p to the r goes to infinity. Thank you for listening. Please email me or the other authors with any questions or comments about our paper.